Hi everyone. In this video we are continuing our discussion on Newman projections, and in the prior video number 01D50 we introduced Newman projections, and we saw that at least for the case of butane there are actually two types of staggered conformations and two types of eclipsed. And in this video, I'm going to clear up a little bit of some of the terminology, some definitions that I didn't get to in that prior video, and really focus on energy. What's more stable, what's less stable. Alright, let us remind ourselves what a Newman projection is. And here we have, I'm going to do, I'll do butane. Okay, so butane, if we draw the line formula or the line structure, looks like this. Okay, I'll draw it zigzag, and I'm going to orient my person, my little stick figure, looking down this bond here. It's the 2-3 bond, carbon number 2, carbon number 3. Okay, according to their point of view, they have a front carbon, they have a back carbon, and the front carbon has a methyl group down here. Actually, if you want, go ahead and pause the video and see if you could draw the staggered Newman projection that this person sees. Okay, so go ahead and pause the video. Okay, so the methyl group is going down to their feet, and we have two hydrogens. On the back carbon, carbon number 3, the methyl group is going up from their point of view, and the two hydrogens are now here. Two hydrogens in the back. What were we doing last time? We were rotating the back carbon 60 degrees. I never really told you what that 60 degrees is. It's not a bond angle, right? A bond angle is between three atoms. So for instance, in this molecule butane, we do have two hydrogens here. Okay, you know that that carbon is tetrahedral, so this bond angle is 109.5, and that bond angle is defined by three atoms. The bond angle of carbon, carbon, carbon. So the bond angle is defined by three atoms. This angle is not a bond angle because if you look at this carbon here and this hydrogen, the relationship between this carbon and this hydrogen, that's 60 degrees. But look how many atoms there are. Carbon, carbon in the back, carbon in the front, hydrogen to the right. So this is an angle that's defined by four atoms. The carbon, methyl, the carbon in the back, carbon in the front, and the hydrogen. That angle, okay, is actually 60 degrees. And that's called a dihedral angle. Okay. So I know this arrow is indicating that I want you to move it, but forget about the arrow. If I said what is the dihedral angle of CCCH, it's 60 degrees. So how do you want to think about that? I have two playing cards. Okay, a dihedral angle is defined by planes, two planes. So the two playing cards are perfectly aligned, and I would say that is a 0-degree dihedral angle. Now if I take, for me it's easier, maybe it's easier in the back. I take the back card and I start rotating it. Okay, do you see how I rotated it? And if I go this far, the dihedral angle is 90 degrees, 90, perpendicular. It's the angle made by the two planes. So we have a plane defined by 3 points, CCC, and a plane defined by another 3 points, CCH. That's the dihedral angle. So you could think of it that way. And we have many dihedral angles. I could have asked you for the dihedral angle of C, 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 C. That's a full 180 degrees. for the dihedral angle, again, formed by the 4 carbons. Not a bond angle, it's an angle made by the planes. Now, I know the carbons are all lined up, but for this carbon to be behind this carbon, you have to rotate it 180 degrees. So I know it looks like, if you're doing the card analogy again, it looks like this. But really what the 180 means is that we take the atom in the back and we go all the way around so they're lined up again, right? It's just an about face when you do a 180. Okay. Don't worry too much about that. I think it will become clearer as we do more drawings. But if I now do the actual rotation, okay, to make this methyl group underneath here, then you have what's called eclipsed. We keep the front carbon the same. Okay. Draw me the eclipse now version where we move this methyl group 60 degrees, or you move this plane a dihedral angle of 60 degrees. Go ahead and pause. Okay. So if you rotate the back carbon 60 degrees, your now methyl group now is underneath this hydrogen, and then we have these other hydrogens in the back. A little bit sloppy, but that is sufficient enough to tell the grader that this is eclipsed. And now our methyl group is here. If we have a set point, and we consider that 0 degrees, okay? Because right now, if I take a look at this, the dihedral angle made between this carbon, hydrogen is 0 degrees, so right on top of each other. But the dihedral angle of the methyl groups, carbon in front, carbon down here, that's not 0. That is 120. Okay, 120. And you'll get used to this as we go through this video. So that's dihedral angle. It's the angle made by the 2 planes that are defined by 2 sets of 3 atoms, the CCC in this case and the CCH. But what I'm also concerned about is, it's a little bit crowded, but we have here staggered, and here we have eclipse. Okay. We did this in the previous video. We drew the 4 main conformations, but let's go ahead and do it again. Another 60 degrees. Right? If I did 120, I would draw the arrow all the way to this carbon. Right? That's 120. You know, a full circle is 360. 120, 120, 120. Okay? So we're toggling in between staggered and eclipsed. And if I know that I'm going to draw a staggered conformation, why don't I go ahead and draw the template for that? Okay. And then, okay, I'm thinking ahead now. I'm going to ask you guys to do it. If I do another 60 degrees, I want us to draw the eclipsed. So I'll draw the eclipse template. Okay. So eclipse looks like that, and there. Okay. Hopefully, again, your drawings are clear enough that I know if I'm grading your exam if something's staggered or eclipsed. So draw me this staggered and this eclipse. Pause the video. Okay. Well, if I'm keeping the front carbon steady, why don't I draw what I know? Okay, be careful here. That methyl group is off of this line here. CH3. Oh, where's the H's? An H here and an H here. So I drew the 3 things coming off of that front carbon. Now let's go back to the eclipse, and I move that methyl group 60 degrees. So now it's here. Bottom left. Sorry, bottom right. And then if I move another 60 degrees, I get the methyl group underneath this methyl group. Look at what I'm going to do. I'm going to push the hydrogens to the left because there's little space to its right. But that's still a methyl group. CH3. The others are H's. Staggered, eclipse. Okay. Take a look at these two staggered conformations of the Newman. We have the methyl groups far apart, and here I have the methyl groups close together. Those two will have different energies, different stabilities. And if I zoom out, let's figure out which staggered is the more stable staggered. Okay, here's the first staggered that we drew, and I'm going to make the molecule model like that. Okay, if I tilt it on its side, it looks like this. See, the methyl groups are far apart and it's zigzag, just like we had this drawing right here. But as I move this, 120 degrees, the back carbon. So where's 60? 60 is there, eclipsed. Another 60 is like back to the staggered. Okay. Now when I put it on its side, not twisting it, but just putting it on its side, see how the methyl groups are closer together? And since they're closer together, as this bond rotates and this bond rotates, the hydrogens are actually coming very close together and we're getting repulsion. Now, if these models were exactly like atoms, this would be a big sphere. You know, atoms are spherical. So actually, you're competing for the same space, these two hydrogens. When you are in a staggered position, lost it, when you're in a staggered position like this. Okay. So the main point for now is that this is less stable. Okay. This is the most stable. Staggers are more stable than eclipse, and this stagger that I'm pointing out is more stable than this one. This is the most stable. But what is the strain? Okay, what do we call it? You know, before, in our previous video, 01D50, we discussed torsional strain. And torsional strain is strain that's felt by the molecule when bonds are close together because we have electron repulsion. And bonds are closer together when you have eclipsed conformations. So you could call this eclipse strain, but everyone calls it torsional, but people are thinking eclipse. Whenever you have a molecule that has eclipsed bonds, you have torsional strain. But this is not eclipsed, but it's still less. It still is more unstable, or still less stable than this one up here. Remember what we said? If something is less stable, it has more energy. It's higher up on the energy diagram. The strain here is actually bumping strain. And the bumping strain has a specific name, terminology, steric, S-T-E-R-I-C. And you could think of that as, I'll put this also in quotes, you could think of this as bumping strain. It's not the electrons that are repelling each other, it's the actual bumping of atoms that's making this conformation less stable. So the torsional strain is a repulsion of electrons in the bonds, right? See these two bonds here, they're eclipsing this bond right here, repulsion. Over here it's actually physically bumping into each other, so this molecule in this conformation is less stable than this up here. There's actually a special name now for these two staggered conformations. If you recall, before we talk about the two names, ethane, right? Ethane, which only has hydrogens off of those carbons, the two staggered, or the staggered position only has one energy. They're not split up into two energies because, well, I'm not going to draw it, but if you visualize, imagine these two are hydrogens. Okay, we have that staggered, and that's going to be the same energy as this staggered, because if we have these two as hydrogens, it's the same looking molecule, right? Imagine that these two methyl groups were hydrogen. So ethane only has one staggered energy level. There are two different energy levels for the staggered. The one that's more stable is called staggered anti, and I'm going to put a comma here. Okay, or you could call it anti-staggered or staggered anti without the comma. Doesn't matter. Just know that this is a special type of staggered conformation, which is more stable than this one. This is interesting. This is actually called Staggered Gauche. Right? Those of you who've taken French, gauche means left. Okay. But it also means awkward. Like if you're, it's like it's the wrong footing if you're left-footed. Or, well, we'll just say awkward. Another way you could think of awkward is it veers. It's veering. So we could think of it as a veer to the side. Okay, it's the veering to the side. So this methyl group is veered just slightly to the side of this methyl group here. Okay, it's still staggered. It's still definitely more stable than the two eclipse. Now, well, if there are two energy levels for the staggered conformations, what about the eclipse? Well, yeah. Take a look at that eclipsed. Okay. Here, the model is staggered. Okay. If I move this carbon another 60 degrees to make it eclipsed, ouch. E. Take a look at how close these hydrogens are now when I put it on this side. They're right there. They're definitely going to be bumping in real life when you have, when you space fill these, when you give them some bulk. Hydrogen's not this tiny relative to the molecule. It's bigger. You could have bumping. So this conformation has very severe torsional strain and steric strain. It even has more steric strain than this one right here. Okay. This one down here is the least stable. We have 4 conformations here. We're going to put them on a diagram. Okay. We're going to label them. Well, before I label them, let me make the point here. I've always thought this is a little bit strange, but there's no special names for the two eclipsed. This one is less bad because, see, the two methyl groups are at least far apart from each other. You still have torsional strain, but at least we don't have steric strain between the two methyl groups. Okay, these two hydrogens don't have steric strain because they're tiny. They're not literally bumping into each other, even though on paper they look really close. Okay. We're going to put these 4 drawings on an energy diagram. And depending on your professor, okay, the starting point could be different. I like to have the starting point be the most unstable, the one with the highest energy. So we're going to have an axis. I should have started a new page. This is a little bit tight. And we have the x-axis. Okay. Most likely you will be responsible for drawing an energy diagram. For my energy diagrams, I have 4 dihedral angles. And we're going to start with 0. 60, 120, 180. Okay. If we go further to like, what is this? 240, 300, 360, we're just repeating the same conformations. I want 0, for me, by definition, to be the highest energy, right up there. Okay. So think about which of our 4 molecules has the highest energy. It's the one that's least stable. High energy, least stable. So why did I put here 0 down at the axis? 0 degrees, 60 degrees, 120, 180. These are, again, dihedral angles. Well, I'm going to define 0 to be the two methyl groups on top of each other. And that's going to be my starting point, 0. Okay? Because, well, we have our two playing cards, and that's the 0 dihedral angle if we're focused on the atoms that are right on top of each other. Okay. I'm not going to draw all the Newman projections, but I'll draw the 0, the most unstable. Okay. And I am going to make the methyl groups on top. Okay, it's a little bit tight, but see, this is super tight actually because it's the least stable, and my methyl groups are eclipsing each other. And here we have hydrogen, hydrogen. Okay, and I have the dot up there. What I would do if I have to draw the other four is I would hold one of them steady, and I'm going to hold the front carbon steady, and I'm going to move the back carbon 60 degrees. We're going to toggle between eclipsed and staggered. So if the front carbon is steady, not moving, we have this. And the back carbon moved 60 degrees, and we have the methyl group now off to the side at the 2 o'clock position. See, right now, I know it's a little bit off to the left, but this is at the 12 o'clock position. So we move it 60 degrees to the, is it 2 o'clock? The 2 o'clock position. We have a staggered. But remember, is this the most stable staggered? It's the gauche. See how we have the two methyl groups close? Not eclipse, just close in the staggered position. A lot of times when they want to show bumping strain, people do this. Like literally the spheres that are carved out by these two methyl groups are bumping into each other. They're trying to occupy the same space. Remember, the staggered is always more stable than the eclipse. So I'm going to put the dot lower. Not so low, because I want to reserve the lowest spot, right, for our staggered anti. So I'll put a little note here. This is the gauche. Yeah, should have started a new page. Okay. Another 60 degrees. You know what can help us keep track? How about we do this? Why don't we put a square around the methyl group? So that, heck, why don't we put a square around the other methyl group, pink and green? So do you see how I can consider that 0 degree dihedral? And now here's the green, and we move the pink 60 degrees. So the relationship between these two methyl groups is now 60 degrees. Let's make it 120. We went from eclipse to staggered gauche to another eclipse. Now, is this eclipse going to be as bad as our original? Let's see. Okay, that methyl group moves 60 degrees counterclockwise. Okay, it's eclipsed, but it's not as bad as this eclipse. Okay. Here's your methyl group in the green, methyl group in the pink. Where do you think that dot will be now? Would it be higher than this dot or lower? Well, this molecule, this conformation is more stable than this eclipse, but it's less stable than staggered because all eclipses are less stable than staggered. So we're going to put it in between these two dots in terms of the level. Okay. And then the last one, I'll let you draw this on your own. No, let me complete the drawing. How am I up with time? Okay. Methyl, H, oh, H, there we go. The pink boxed methyl is now down there, the green box methyl was always at the top. That's the most stable. It has the least strain. There's no torsional strain, and there's actually no steric strain. Put that dot as low as possible. If you think about now connecting these dots, you have the top of the hill, steep drop, plateau, the valley. Plateau, rise, plateau. Plateau, fall, plateau. And then I like to make sure that the grader knows that these four are on all different levels. 4 different energy levels. Okay. That's an energy diagram, the full energy diagram. Now I'm not telling you how much energy it is between the dots, right? That would tell me how much energy I need to pump into the molecule to force it into a higher energy state. Okay, so if I start in this conformation, I have to add energy. I have to add energy to get to this state, right? And the higher the energy, is the less stable. Dots that are very high are states that are very unstable. Now, in the last couple of minutes, I'm going to suggest a few molecules that you should do on an energy diagram. Ethane. The thing with ethane is our 2 eclipsed conformations, the 0-degree dihedral and the 120-degree dihedral angle, they're identical in energies because mentally, replace all of these boxes with hydrogen. Okay? If you replace all of these with hydrogen, which is what would happen with ethane, do you notice that we have the 2 identical drawings? They're both eclipsed, and it's a hydrogen eclipsing a hydrogen in each case. Okay, so this dot would be on the same level as this dot for ethane. So I'll challenge you to draw the energy diagram with the Newmans, right? With the Newman projections. 4 Newman projections. 1, 2, 3, 4. What about another molecule? What about this molecule? I know we haven't worked with other atoms besides carbon and hydrogen early in this series, but what if I put a big halogen atom like bromine? And here I'll put bromine. I might be making this more complex than normal. Here's my stick figure. Okay, so I have to tell you which carbon-carbon bond to look down, and I'll tell you to look down this carbon. Okay. I'm not going to name this molecule. We, at this point, haven't done any nomenclature with molecules with halides, like bromine, chlorine, but you can still do the Newman projection. But I do have to tell you how these 2 groups are oriented. Okay, right? Make it look tetrahedral, and obviously for here we have 1 hydrogen wedge and 1 hydrogen dash. Okay, I'm wondering whether it's going to look like the energy diagram is going to look like the same for ethane, or if it's going to look like the one for butane. And then one last one, and then I'll end this video. What if we had the 2 bromines here on the same carbon? I wonder what the energy diagram will look like in this case. Okay. And you could try those at home. Energy diagram with the 4 Newman projections with the 4 dihedral angles.